Hello everyone, this is lecture 4 of week 10. So, in the previous two lectures we were looking at the affine scaling method, right. So, if you recall, so we are having this is a method where we actually start from an interior point, right, and try to find a direction, both a descent direction as well as is in such a way that it is, I mean, the point lies inside the feasible set, right, the feasible polytope, right. And we were also discussing about the stopping criterion, right. So, we learnt a little bit about duality, right, and we said that if the primal value and the dual values are close enough, right. So, that is within a tolerance, right. So, in that case we will stop the iterations, right. So, that will be used as a stopping criterion, right. So, yeah, if you recall what we where we ended up in the last class, right. So, please note that so if the primal is min over C minimum of C transpose x subject to Ax equal to b, x greater than or equal to 0, right. So, we saw that the dual is actually maximizing mu transpose b subject to A transpose mu greater than or equal to minus C, right. So, there were a few errors that I would like to correct from where we ended up, right. So, when we write mu transpose Ax minus b, right. So, we would actually get minus mu transpose b and not mu transpose b, right. So, that is because, so if you recall what has happened, it is so we are minimizing C transpose x plus mu transpose Ax into Ax minus b minus lambda transpose x. So, if you differentiate this with respect to x, you get C plus A transpose mu equal to lambda, right. So, yeah, so if you write C plus A transpose mu, so yeah, what this means is that yeah, C plus A transpose mu the whole transpose x minus lambda transpose x is equal to 0, right. So, you have C transpose x plus mu transpose A x minus lambda transpose x, that is 0. So, the remaining part is just minus mu transpose b. So, I mean I made a mistake, I did not include the minus, right. So, yeah, so the problem thus becomes maximize minus mu transpose b subject to A transpose mu greater than or equal to minus C, right. So, suppose I write mu as minus mu, okay. So, note that mu is not constrained, right. So, if instead of mu being 5, if I write it as minus 5 for example, or any mu as minus mu, right. So, now this problem would equivalently be written as max mu transpose b, right. So, because mu has become minus mu, right, and this is minus A transpose mu greater than or equal to minus C. So, multiplying throughout by a minus, you will get A transpose mu less than or equal to C, okay, max over mu, okay. So, yeah, this is more pleasing to the eye than writing maximum of minus mu transpose B, right. So, we will consider this as the dual, okay, fine. So, yeah, the moral of the story is that if the primal problem is min of C transpose x subject to Ax equal to b, x greater than or equal to 0, okay, then the dual is max mu transpose b or b transpose mu, yeah, whichever is comfortable to you, okay, subject to the constraint that A transpose mu is less than or equal to C, okay. So, thus what it means is that if we get a mu in such a way that, so if you look at the theorem, when you have a linear programming problem where a solution exists, okay, then the values of the objective functions of both the primal and the dual are one and the same, right. So, if you actually have an x such that, so if there exists an x which is primal feasible, okay, that means that satisfies Ax equal to b x greater than or equal to 0. Okay. So, if there exists x which is primal feasible and there exists mu which is dual feasible, that is mu satisfies A transpose mu less than or equal to C, okay, and it also turns out that then we have the solutions for both primal and the dual problems. Okay. So, the good part about linear programming is that when you have your primal to be a linear programming problem, the dual also turns out to be a linear programming problem, right. So, yeah, in this case you can see that the primal was, we started with the linear programming problem, the dual also turned out to be a linear programming problem in mu. Okay. So, yeah, one of the ways of finding the solution for the primal is that you find an x that is primal feasible, mu that is dual feasible, and C transpose x equal to B transpose mu. Okay. So, if you can find an x and mu such that all of these conditions hold, then we actually have the solution for both the primal and the dual problems. Okay. So, this is how we actually, yeah, choose the stopping criterion, right. So, if you recall the steps in the affine scaling method, right. So, we start with an initial point, we do a centering, right, and then for the centered vector, right. So, we move along the direction of the steepest descent direction, right, and we I mean not just the steepest descent, I mean it is actually a projection of the steepest descent onto the null space of the matrix A, right. So, we move along that direction, and after moving there we actually decenter it, so that we get back the value in the original space. So, we can keep continuing that until some stopping criterion, and we were trying to figure out the stopping criterion using the duality method. So, we just saw that C transpose x will be equal to B transpose mu if we are if x is the minimizer, right. So, we can stop if, yeah, so I should have written the modulus. So, yeah, we will stop if the modulus of C transpose x minus mu transpose B is less than or equal to some tolerance, say 10 power minus 6. Okay. Yeah, so if it is greater than the tolerance, then continue doing the loop, right. So, when, yeah, x and mu are such that the difference between C transpose x and mu transpose B are within some tolerance, then yeah, we stop, right. So, yeah, this is basically the idea. Okay. Yeah, but we are still not done yet, because, so yeah, it is good that we have got all these theorems, but now what is the value of mu? So, suppose, so let us say you start with some x 0, okay. Yeah, you do the centering, move along some direction, do the decentering, all that is fine, but given an x 0 or x k or any x for that matter, how do I find the corresponding mu, right. So, that needs some particular step, right. So, yeah, that is still something to be solved, we will do that now. Okay. So, if you consider the primal problem, right. So, the primal problem is, yeah, min C transpose x subject to x equal to b x greater than or equal to 0. So, if you write the Lagrangian for the primal, right. So, for the primal I am writing the Lagrangian, which is x, lambda and mu, right. So, you have C transpose x, so for equality we are using mu. So, let us say it is mu transpose A x minus b, Okay. So, yeah, it is good to write b minus ax. Okay. So, yeah, if I had written that in the last class, right. So, instead of ax minus b, I need not have done this taking the minus mu business. Okay. So, yeah, let me do that now. Okay. And of course, this is minus summation lambda xi I equal to 1 to n, right. So, this is the Lagrangian, and so if you want to solve this, right. So, you take the gradient with respect to x, so and equate it to 0. So, what this tells us is that c plus or c minus actually c minus mu transpose A minus lambda, right, should be equal to 0. So, you have, yeah, I think this should be A transpose mu, sorry, right, yeah, okay. So, yeah, so then you will have A transpose mu plus lambda equal to C. Okay. So, this should be satisfied if x is the minimizer, right. So, you should have mu and lambda in such a way that A transpose mu plus lambda is actually equal to C, right. So, and yeah, so we also have the complementary slackness conditions where you have lambda I xi equal to 0 for all I equal to 1 to n, right. So, yeah, I mean this is all part of KKT conditions, I am not writing anything new. Okay. So, we have the gradient of L equal to 0 and lambda I xi equal to 0 for all I, right. So, what this tells us is that at least one of lambda I or xi has to be 0, right. So, if xi is positive, okay, that means lambda I is 0. Okay. So, we will actually have A transpose mu equal to C. Okay. So, if xi equal to 0, then A transpose mu of I equal to or minus C of I equal to 0, okay, minus C of I equal to 0, right, because sorry, if xi is positive. Yeah, so if xi is positive, then lambda I is 0. So, if lambda I is 0, then A transpose mu of I minus C of I equal to 0, right. So, what I can write is that we have xi into A transpose mu of I, so yeah, minus C of I equal to 0, right. So, for each component I, so this is true for all I. Okay. So, if xi is positive, then this is 0. If xi is 0, yeah, the product is anyway 0. Okay. So, this is true for all I in 1 to n. Okay. Or in other words, if I, so if capital X is diag of x, okay, I can write this in terms of a matrix, right. So, then we have capital X into A transpose mu minus C equal to 0. Okay. So, this is a condition that actually relates x and mu. Okay. So, that is the reason we have written down all of this. Okay. So, what we can actually do is, so now that we have an equation that relates x and mu, right. So, we can actually find the least square solution, okay, for which mu actually satisfies x into A transpose mu minus C equal to 0, right. So, this is when x is the solution, right. So, x and mu are the solutions of the primal problem, yes, then you will see that capital X into A transpose mu minus C is equal to 0, right. So, we are actually, so if x is not the solution, right. So, we are actually going to choose a mu in such a way that, yeah, so this is actually satisfied in the least square sense, okay, in the sense we choose a mu such that, okay, let me possibly write that down, okay. Yeah, so what this means is that x A transpose mu minus x c equal to 0, right. So, instead what we are going to do is, can we find mu such that x A transpose mu minus x C is minimized, the norm of x A transpose mu minus x C is minimized. Okay. So, this is, I mean, so yeah, I am not going to solve yeah, so you can take squared, no problem. I mean, with or without square does not have any difference. Okay. The solution does not have any difference, right. So, yeah, I am not going to derive this, but I mean it is easy to see that the answer is the following. So, if x A transpose were invertible, yeah, I could have just written x A transpose inverse x C. Okay. Yeah, but x A transpose need not even be a square matrix, right. So, note that A is an m cross n matrix, A transpose is n cross m and x is n cross n, right. So, it is actually an n cross m matrix, it is a rectangular matrix and not invertible, right. So, what am I going to do is multiply on both sides by Ax. Okay. So, that is going, I mean, so you will actually have Ax squared A transpose mu equal to Ax squared C. Okay. So, what I have done is just pre-multiply throughout by Ax. Okay. Now, yeah, so now you can see that Ax squared A transpose is just an m cross m matrix. Okay. And yeah, it can also be shown that it is an invertible matrix, the rank is m. Okay. So, since the rank of capital A is m, so you can actually show that the rank of Ax squared A transpose is also having a rank of m. Okay. So, thus you will have, yeah, mu is equal to Ax squared A transpose inverse Ax squared C. Okay. So, if x is the solution, okay, then yeah, so you will actually satisfy x A transpose mu minus x C equal to 0, that means Ax squared A transpose mu equal to Ax squared C. Okay. Then you and thus you will actually get mu such that x into A transpose mu minus C is equal to 0. Okay. So, since yeah, x need not be the solution, x could be any arbitrary point, right. So, what we are doing is, I mean, instead of finding mu that satisfies x into A transpose mu minus C equal to 0, right. So, yeah, we are minimizing this quantity, I mean, which is the norm squared of this quantity, right. So, because of which we are getting mu to be Ax squared A transpose inverse Ax squared C. Okay. Now, you can see that when we are given x, we have a value of mu, right. So, now I can write down the steps as follows. Okay. So, suppose when you have a primal problem of this form, right, as given in the first line, minimum of C transpose x subject to Ax equal to b x non negative, right. So, what you first do is you can find the value of mu and check that the steps for the algorithm, I will possibly start writing it in the next page. Okay. So, yeah, steps for the algorithm is the first step is just convert the given LP to its standard form. Okay. Okay. So, we have to initialize x0 as an internal point of the feasible polytope. Okay. And yeah, you can initialize k equal to 0. From here you would have got x0 as well. So, maybe I will initialize, I mean I will write capital X0 as diag of x0. Okay. And yeah, so now I can write mu 0 as A x0 squared A transpose the whole inverse A x0 squared into C. Okay. Yeah, a big formula, but nevertheless, so this is something that you need to find. Now, while modulus of C transpose x minus C transpose x k minus B transpose mu k is greater than tolerance. Okay. So, yeah, you can see that yeah, so if it turns out that C transpose x 0 minus B transpose mu 0 is less than or equal to tolerance, we can stop there. Okay. Fine. So, yeah, so here we will write down whatever we had initially. So, you need to first do the centering, right. So, centering is, so you have yk equals xk inverse little xk, right. So, and then you need to now choose the direction, right. So, the direction is actually yeah, so this will anyway be the one vector, right. So, it is a vector of n ones, okay. So, you can recall what we did here, right. So, xk inverse xk is always the one vector, okay. So, all right, and the next one is you choose the direction. Direction is just the projection of minus c onto, minus c is the steepest descent direction, right. So, you project that onto the null space of the matrix A, right. So, because of which you will actually get minus of I minus A transpose minus A, the whole multiplied by C, okay. Okay. So, okay, here there is a catch, okay. So, yeah, if you have okay, so there is an error in what I have written here, okay. So, yeah, this is correct if we are actually using dk for in the xk space, right, okay. So, this is correct if we are actually using dk for the xk space and not the yk space, right. Yeah, in the yk space we need to do a little bit of change, okay. So, let me do that now, yeah, I will do it here, okay. Yeah, so I am writing the algorithm here since I need to do something, yeah, I will finish it here and then come back to the algorithm, right. So, note that if you consider this particular problem, min C transpose x subject to Ax equal to b, x greater than or equal to 0, right. So, here, yeah, the projection of minus C onto the null space of A is minus I minus A transpose inverse A into C, right. But now in the Y space this is slightly different, okay. So, yeah, how does this change? It changes as, so if you recall what is y, y is k inverse x, right. So, x is actually, so yk is xk inverse x, so xk is capital Xk into yk. So, I will substitute capital Xk into yk here, right. So, this will be C transpose capital X into y subject to, so this x again becomes A x y equal to b y, yeah, of course x y greater than or equal to 0, but since x capital X is greater than or equal to 0, this is the same, okay, it is not going to change, okay. So, you can see that C has become sorry, C transpose has become C transpose x. So, that implies C will become x transpose C, but yeah, x is a diagonal matrix. So, x and x transpose are the same. So, this is x C, and similarly A has actually become A x, okay. So, now the projection becomes minus I remains the same, but now A has become A x, right. So, A transpose is x transpose A transpose, yeah, but for x I do not need to write transpose, x A transpose, and this is A x x transpose, x transpose again is x, so x squared. So, A x squared A transpose inverse, okay, and here again A becomes A x and C becomes x C, okay. So, yeah, now it, instead of this minus of I minus A transpose inverse A into C, we have to write minus of I minus x A transpose A x square A transpose minus A x into x C, okay. So, you might be baffled by seeing such a large expression, okay, but you need not be, because this is so yeah, let me simplify this. Okay, so this is actually yeah, minus xc minus, so you can see that this part is mu. Okay, so you have, so this plus x A transpose mu. Okay, so that is just x into A transpose mu minus c. Okay, so this is what we are going to choose as dk. So that is the reason I did all this. Okay, so your dk is just going to be x into A transpose mu minus c, mu k, I will write all of that. Okay, so x k into A transpose mu k minus c. Okay, so I am just copied down this x into A transpose mu minus c. Okay, now if you go back, you can see that I have written yk equal to 1 plus alpha dk, actually alpha k dk. Okay, and I told you that alpha k we will see about this a little later, right. So we will do that now. Okay, so I will write this down, yk plus 1 is yk, which is 1, right. So 1 plus alpha k dk, but what is alpha k? How do I choose alpha k? Okay, note that yk plus 1 actually has to be greater than or equal to 0, right. So if we want 1 plus alpha k dk greater than or equal to 0, right. So then we need alpha k, yeah, alpha k dk greater than or equal to 1, right. So alpha k is less than or equal to, sorry, minus 1 this is. Okay, so yeah, alpha k is minus 1, and so yeah, I mean these are vectors, minus 1 is a vector, dk is a vector, right. So yeah, so this must be less than or equal to minus 1 by dk j, right, for all dk j such that it is negative, right. So maybe yeah, for all j such that dkj is negative. Okay, so this is what I want. Okay, otherwise we cannot assure 1 plus alpha k dk is greater than or equal to 0, right. So yeah, so I am just going to choose alpha k as, sorry, alpha k as min of, yeah, j such that dkj less than 0 minus 1 by dkj. Okay, so yeah, I can write that here. Alpha k is, so you consider the set of all indices for which dkj is less than 0, and among that set you are going to minimize the quantity minus 1 by dj. Okay, so we have chosen dk, we have chosen alpha k, and yk plus 1 is just 1 plus alpha k dk, and xk plus 1 is the decentering process, which is capital Xk into 1 plus alpha k dk, or yk plus 1, but yeah, both are the same. Okay, now given that xk plus 1 is found, you can write capital Xk plus 1 as the diag of xk plus 1, and mu k plus 1 as A xk plus 1 squared A transpose inverse A xk plus 1 squared C. Okay, and you write k equal to k plus 1. Okay, yeah, now you can write the output x star equal to xk. Okay, so yeah, so this is actually the complete algorithm for the affine scaling method, right. So yeah, we will discuss this once more in the start of the next lecture, and then we will yeah, work out some examples. We will start with some examples in the next lecture. Thank you.